Greetings, this is Advait Karnal, and today we are going to talk about ocean simulation and buoyancy interactions as a part of the game physics development basics activity. So we begin with ocean simulation and the game physics within it. So oceans are basically a collection of nearly infinite particles of water. So a sea or an ocean or a big lake also can be considered as a nearly infinite particle system. So within a closed system, the liquid would generally settle and the surface would become still. But however, in the real world, we know that the surface tends to be non-uniform and it cannot be still all the time due to wind and air, which is also fluid. And the movement of wind and air above the surface of a water causes turbulence between the interfaces of these two fluids, causing what are known as waves, and these waves are basically a result of turbulent fluid currents between the air and the water interacting with each other. So let us assume that a general case is where a fluid body settles on top of bedrock, that is the ground, and on top of it we have a free fluid, that is the sea, and above that we have the sky, which has wind. So in a real world scenario, wind is not something that is stationary, air is not stationary, the particles move around due to energy distribution. So here you can see in the diagram we have a arrow here indicating the direction of the velocity of wind in the sky region, that is in the air, in the atmosphere. So this fluid, that is the air, also interacts and has an interface, that is the two surfaces interact with each other where the sea and the sky meet. So this region is called a turbulent region and is known as the interface between the two fluids. So as and when the fluid in the air moves at velocity Vw, it causes turbulence here on the surface, and this turbulence leads to motion of particles in the water, and this motion also causes a general velocity direction to be formed due to this wind velocity in the same direction. So here we have what is called a progressively decreasing velocity, as in how the depth decreases in the fluid of water. The velocity also decreases due to slipping between the particles slowing down. So you can see as and when the layers of the water become deeper, the velocity decreases until it reaches the second turbulent region where the solid interface meets with the fluid interface, that is the bedrock or the ground, interacts with the water. So this region is also known as a turbulent region, where this velocity is not determined by the speed but rather by the relief or the topography of this bedrock. So this can be modeled in scenarios where it is required for fluids like air and water to interact in a ocean and sky environment. So these fluid waves, these surface fluid waves, are modeled by equations known as the Stokes wave function. So as per Stokes wave theory, it is used to simulate waves which are of a bulk fluid, that is like an ocean or a sea, which have a moderate to infinite depth. So the reason we take depth into account here is because we need to understand how much of a role the bedrock plays in the wave formation. So in shallow waters, there is a lot of geometry that needs to be taken care of. However, in moderate and infinite depth, we can simply use a low order of the expansion of the differential equation, that is the Stokes wave function, and using that we can find the wavelengths and the required phase for the fluid waves. So in shallow water, we use what is called a Bosine-esque approximation, which is more realistic for that scenario. So here you can see that we have a function called eta of xt. X is the position, that is the position in the x direction, and z is the vertical displacement. So eta gives us the required function as a result of the horizontal displacement gives at a particular time. So at a time t, at every position x, we get a z value. So here we have the free surface elevation, that is eta. Along with that, the velocity potential, which is the potential that each particle on that surface has, is known as phi, denoted by phi, which is a function of both the vertical, horizontal, and time components. And then we have what is known as the phase and the phase speed. So phase is basically the angle at which the wave moves around, and the phase speed is the speed at which that changes. So this gives a very realistic approximation of a wave. However, the reason Stokes wave function is known to be a little cumbersome in applications in game physics is because it requires a lot of computational power to calculate in real time. So to ensure that we can have a more efficient way to implement game physics in engines, we can use what are known as Gerstner surface waves. So Stokes waves tend to be more accurate. However, Gerstner surface waves are much easier to implement and have a more realistic modeling compared to Stokes due to its inclusion of x and z and the y coordinate. That means the height not only moves as a sine wave, like here you can see in the diagram, the top part is a normal sine wave. So we have a vertical displacement at every horizontal position. However, here you can see that we have a radial displacement based on an original position of the surface. So we can see here that the equation has three components. We have an x component, a z, and a y. So the x and z takes care of the planar surface, that is in the surface horizontal to the sea, and y takes care of the vertical displacement of the waves. So these three are a function of alpha, beta, and t. So alpha, beta are basically the initial positions. That means the center of these radial interfaces are what is alpha and beta. So the height is automatically taken as 0 here because all of these are at the same height initially. Alpha beta gives us the world position or the position in the sea at each vertex. And based on these initial positions, as the time goes on, we get a new displacement for x, for z, and for y. So here in this equation, we can see that theta m is given by this equation. So theta is the angle at which this particular displacement, this red line, is calculated by theta m. So from here, from this very first frame, you can see particle from the first vertex, this rotates. So this is theta m. So here m denotes the number of wave components. So you can have many components in this wave. That is another advantage to using Gerstner surface waves as a modeling theory instead of Stokes. So you can have multiple components of waves, and each wave component can have a different amplitude, a different phase, and a different wave number along with a separate angular frequency. So now let us move on to the implementation of a potential implementation of such ocean waves. So here we can see that in the game physics engine, we can use meshes to actually code the Gerstner surface waves as a mesh displacement. So the height of each point in the mesh is calculated by the y function, and the xz is calculated by the xz function. So here you can see that the shaded wireframe is on the slide. So this takes in an x and y position in the world and returns the mesh at each point. And when we apply a shader to it, we can configure the colors and we can get a beautiful looking sea which has waves in it. Now moving on to the second part, that is the buoyancy interactions. So buoyancy refers to an upward force that is exerted by any fluid on an object which is immersed in it. So this upward force is generally called an upthrust because it generally acts upwards. However, it need not be so. A buoyancy force is basically a force applied by the pressure gradient of a liquid. So here we have the equation of the buoyancy force F, which is equal to rho Vg. Rho here is the density of the fluid. So the denser the fluid, the more pressure it will exert. The second component is the acceleration due to gravity, which ensures the force of the fluid particles take hold in gravity. So if there is gravity, the particles of the fluid itself are pulled. So that is taken into account. And lastly, the volume of the fluid displaced by the object is taken into account. So here we have the three potential cases. So when an object is immersed in a fluid, it exerts a weight onto the fluid. So it has a weight of mg. So W is equal to mg is the force that gravity exerts on the fluid as per the mass of the object. So that has to be counteracted by buoyancy for the sake of floating of that object. So if that W is same as F, that is mg, the mass of the object times gravity, is equal to rho Vg, then the object floats. That means there is no upward or downward net force. However, if the weight is more, then the object sinks, and the weight is less, the object rises up in the water, even if placed much below the surface of the water. So now that was a very simplistic scenario in which buoyancy acts. In the real world, objects are not always uniform, as in they don't have a smooth surface as per the interface of the fluid. Similarly, they might have a different geometry, like a triangle, which is not uniform in its mass distribution. Similarly, the water, the fluid itself may not have a straight interface based on the gravity normal. So in these cases, what happens is we have torque that begins reacting due to the misalignment of the forces. So this causes what is known as rotational buoyancy. So rotational buoyancy is a concept which takes hold in time. So while the previous general buoyancy is same for each time step, here based on the initial condition, the torque acts, and over time there is some motion that takes place and we reach a stable or a equilibrium. So here in the real world, buoyancy acts at every single point in the contact of the fluid. So that buoyancy force is with respect to the mass and the geometrical shape. So if the net resultant thrust is not at the center of the actual mass, then it causes a rotation. So here you can see in this particular image, we have a triangle which at t is equal to 0 is kept in this very awkward position. So here you can see it's not fully immersed, nor is it stable in its equilibrium. So here you have these two axes which show its geometrical axis. That is, this is the center of geometry in its vertical space, and this is the center of axis in its horizontal place. So the fluid, the net fluid force, that is the buoyancy force, acts here on this axis, whereas the center of mass, that is the cumulative weight, acts at this particular point here. So you can see there is a misalignment in the line and the axis of the acting of the force. So what this does is it causes a torque about this particular axis, and it causes this to rotate in an anti-clockwise manner here. This is because the white arrow, which denotes the buoyancy force, causes rotation in this direction, like that. Okay, and then this torque leads to rotational, and it finally at t is equal to t, which is a final time, which is arbitrarily decided by this torque which is produced, leads to what is called a stable equilibrium, where this particular weight vector acts exactly in line with the total interface of the buoyancy force. So this torque due to axial non-alignment is known as the one which happens due to a non-uniform shape. Secondly, this same thing can happen if you have a uniform shape but a non-uniform volume immersion. That means if you have a square, let's say it's a square which has a uniform shape, but due to waves in the water, one part is submerged more than the other. So here you can see in this image here, this particular part, this particular quadrant in this axis, in this quadrant axis, is submerged more than this bottom left one. That means there is more volume that is immersed here. So therefore, rho Vg at this point will be much more than rho Vg at this point. So therefore, this will cause an imbalance in the at one side and the other, causing more force to react here, and it causes rotation. And finally, at a final arbitrary time t, this is how it will look. So it will align itself with the fluid interface. So interface is this particular curve, that is the surface, and within the fluid it is also the same surface that causes the buoyancy force. So in implementation, we can use what are known as mesh normals to find the normal of that particular point in the water and use buoyancy at that particular point to react as a weight against the object that is floating. So we use a position on the wave or the mesh, and then we find what are known as normals. So here you can see in the image we have the ship. So in the ship we have this particular normal vector which is due to this wave shape like this. So due to this we can find the direction of the force which needs to counteract the weight and gravity. And using the difference in these two, in the water line and the line that is particularly the line perpendicular to the weight vector of the object, we can find the needed rotational torque required to make it realistic in its simulation. So thank you for listening to this presentation on ocean simulation and buoyancy interactions. Thank you.